there is a planet right now being physically torn apart by its own star, orbiting so fast that a full year there lasts just over 1 Earth day, and the star is winning. Somewhere else in the galaxy, a world the size of Jupiter weighs almost nothing, and scientists have been arguing about how that is even physically possible. These are not simulations or theories. These are confirmed planets found by real telescopes, and every one of them breaks rules that planetary science spent decades believing were settled. When astronomers first began discovering planets beyond our solar system in the 1990s, most expected to find systems that looked roughly like our own. Small, rocky planets close to their star, larger gas giants orbiting farther out, everything moving along calm, nearly circular paths. What the data revealed instead was something far stranger. Thousands of exoplanets have now been confirmed, and many of them follow none of the patterns any model predicted. The universe, it turns out, builds planets in ways no textbook had fully prepared scientists for. And the more telescopes improve, the stranger the picture gets. The first planet worth looking at closely is called WASP-12b, located approximately 1,200 light-years away in the constellation Auriga, and it is in the middle of a slow, measurable death. Since its discovery in 2008, the time interval between each of WASP-12b's transits across its star has been shrinking, with the decay rate refined in 2022 to 29.81 milliseconds per year, corresponding to an estimated remaining lifetime of 3.16 million years before the planet is consumed by its star. That might sound like a long time, but in cosmic terms, WASP-12b was essentially discovered in its final moments of existence. To understand why this is strange, it helps to understand what WASP-12b actually is. It belongs to a class of planets called hot Jupiters, gas giants that orbit their stars at incredibly close distances. WASP-12b has a mass of 1.4 Jupiters, orbits at a mean distance of just 3.1 stellar radii from its host star, and its radius is 1.79 times that of Jupiter, a size unexpectedly large for a planet of its mass. The tidal forces from that proximity are so extreme that the star's gravity has stretched the planet into the shape of an egg, while its surface temperature sits at approximately 4,000 degrees Fahrenheit. Planet formation theory says gas giants must form far out in the solar system, in the cold outer regions where the raw materials exist. Something drove WASP-12b inward, a process still not fully understood, and it ended up in a place where it simply cannot survive. That naturally raises a question. Is WASP-12b a rare accident, or is this kind of orbital destruction something the galaxy produces regularly? That answer turns out to be more unsettling than expected. But it requires looking at a completely different kind of planet first. About 210 light-years away, in the constellation Virgo, there is a planet that looks enormous from the outside, but is almost weightless by any meaningful standard. WASP-107b has a diameter 94% that of Jupiter, but carries only 12% of Jupiter's mass, placing it firmly among what astronomers call super puff planets, a category defined by extraordinary size and almost impossibly low density. It orbits its host star almost 16 times closer than Earth orbits the Sun, completing one full orbit every 5.7 days, and sits 7 times closer to its star than Mercury is to our Sun. For years, scientists could not explain why WASP-107b was so swollen. A planet orbiting that close to its star's radiation field should not retain an atmosphere anywhere near that large. Data from the James Webb Space Telescope revealed that the planet has a hotter interior than previously estimated, driven by tidal heating from its slightly elliptical orbit, and a more massive core than scientists originally assumed, helping to explain the inflation without resorting to unusual formation theories. Then came the clearest evidence yet of what is actively happening to this planet. JWST observations captured continuous helium absorption, beginning approximately 1.5 hours before the planet itself passed in front of its star, revealing an extended atmospheric cloud so large that it was already blocking starlight well before WASP-107b arrived. researchers also identified water vapor, sulfur dioxide, carbon monoxide, carbon dioxide, and ammonia in the atmosphere, while finding no detectable methane, despite JWST being fully capable of identifying it, providing chemical evidence that the planet formed far from its current orbit and migrated inward, where intense radiation is now stripping its gases into space. What remains is a planet actively leaking its own atmosphere into space, slowly shrinking in ways that cannot be reversed. And if a planet the size of Jupiter can be reduced to almost nothing by its environment, the next planet raises an even more uncomfortable question about what drives that process. HIP 67522b, located about 417 light-years away in the constellation Centaurus, is a hot Jupiter orbiting a star that is only about 17 million years old, which in stellar terms is extremely young, and the planet completes one full orbit every 7 days. Those facts alone would be remarkable, but what makes this planet genuinely difficult to explain is not just what the star is doing to it, it is what the planet appears to be doing to its star. The planet's extremely close orbit connects to the star's magnetic field lines, triggering powerful flares on the star's surface. Researchers observed that flare activity ran approximately 9 times higher during the portion of the orbit immediately following the planet's transit, across 5 years of observation, with each flare blasting the planet with intense high-energy radiation. Webb observations revealed that HIP 67522b is Jupiter-sized, despite weighing only roughly 15 to 20 Earth masses, making it one of the least dense planets ever confirmed, with the magnetic interaction now believed to be a major driver of that extreme inflation. The planet is not simply suffering from its environment, it appears to be playing an active role in generating the energy that is destroying it. Scientists predict that if atmospheric erosion continues at its current rate, HIP 67522b could shrink from its current Jupiter-sized diameter down to something resembling Neptune in roughly 100 million years. What exists right now is a snapshot of planetary transformation already in progress, and it raises a question that cuts across every hot Jupiter ever found. How many of the small, dense planets discovered close to their stars were once something much larger before the radiation stripped everything away? HR 5183b is a gas giant approximately 103 light-years away, roughly 3.2 times the mass of Jupiter, on a highly eccentric orbit with a measured eccentricity of 0.84, one of the most extreme values confirmed for any known planet. Its orbit carries it from within the equivalent of Jupiter's orbital distance all the way out beyond the equivalent of Neptune's orbit and back again in an estimated period of 45 to 100 years, following a path more typical of a comet than a gas giant. Planets form from flat disks of gas and dust surrounding young stars, which naturally produces nearly circular orbits. For HR 5183b to be on such an extreme path, it must have received a powerful gravitational kick from another object, and the most plausible scenario proposed by the Discovery team is that the system once contained a second planet of similar size. When the two came close enough to each other, one was ejected entirely from the system, while HR 5183b was thrown into the extreme eccentric orbit observed today. As Professor Andrew Howard of Caltech, who led the California planet search that found the planet, described it, this newfound planet basically would have come in like a wrecking ball, knocking anything in its way out of the system. Sarah Blunt, first author of the Discovery study, noted that it is unlike the planets in our solar system, but more than that, it is unlike any other exoplanets we have discovered so far. The planet that was ejected left no trace. It could be drifting through interstellar space right now with no star, no light, no warmth, and no way to detect it with any technology currently available. Looking at these 4 worlds together, a pattern becomes impossible to ignore. WASP-12b shows that gas giants can end up in orbits so close to their stars that tidal forces devour them in real, measurable time. WASP-107b shows that a planet can be simultaneously enormous and nearly weightless, and that Webb can now observe a planetary atmosphere leaking into space in unprecedented detail. HIP 67522b shows that a young planet can become physically entangled in its star's magnetic activity in ways that accelerate its own destruction. HR 5183b shows that the violence of early planetary systems can leave scars so deep they are still visible in the shape of an orbit billions of years later. The models planetary scientists built before the age of exoplanet discovery were constructed around one example: our own solar system. Every planet in it shaped the theories, and every theory predicted systems that largely resembled it. When telescopes began revealing what the rest of the galaxy actually contained, that picture came apart quickly. As Professor Howard put it, at the time of the HR 5183b announcement, Copernicus taught us that Earth is not the center of the solar system, and as we expanded into discovering other solar systems of exoplanets, we expected them to be carbon copies of our own. But it has just been one surprise after another in this field. The planets described here are not the only ones that challenge current understanding. They are simply the ones where the evidence is clearest and the contradictions are sharpest. As telescopes improve and detection methods grow more sensitive, the catalogue of planets that do not fit existing models continues to grow. And each new entry in that catalogue carries the possibility of forcing another rewrite of what scientists thought they knew. What the data keeps returning to is a simple but uncomfortable truth. The universe is under no obligation to build planetary systems that are easy to explain, and it appears entirely uninterested in doing so. Every anomaly solved opens the doors to another, and every model refined by one discovery is tested again by the next. The pattern, more than any individual planet, is what makes this field impossible to look away from.